Let us start our discussion today on economizer. What is economizer? It is nothing but a heat exchanger which rises the temperature of feed water, leaving the highest temperature feed water, heater to about saturation temperature corresponding to the boiler pressure. So we have to keep the uh, exchanger, we keep the feed water, keep the temperature of feed water, leaving the highest pressure feed water heater to absent about the saturation temperature corresponding to boiler itself. The method is just 1 second. Highest, leaving the highest pressure feed water heater to about saturation temperature pressure. So what we are doing, we are heating the feed water by this type of heat exchanger, where we have to rise the temperature of the feed water in the heat exchanger. The it should be the highest temperature should be account as per the saturation temperature corresponding to boiler pressure, where every pressure of a fluid like steam, it corresponds to saturation temperature, means as per this pressure the maximum up to for 100% saturation a particular temperature is Z. 100% saturation of vapor inside the steam, inside the fluid water, we have to give a certain rise to a certain temperature. This certain temperature is defined as saturation temperature, where the amount of water is fully saturated with steam, and this saturation temperature depends to a large extent on the compression of the pressure applied to the boiler itself. Now, this is this heat exchanger. The supply of heat is done by the hot flue gases existing as last superheater or heat reheater at the temperature varying from 372 to 550 degrees centigrade. It is nothing also works like a one type of superheater or reheater. It is also heating like superheater and reheater, the the liquid water or liquid steam, naturally liquid steam, or if a mixture of liquid steam is totally converted to steam to a temperature varying from 350 degree to 370 to 540 degrees centigrade. Here up to a maximum temperature generally varies from 7 to 350 degrees centigrade. The term economizer used because throwing out of such high temperature gases involves a great deal of solar energy losses. By utilizing the three gases, these hot flue gases, for heating feed water, for higher efficiency, better economy are achieved. Which means, why you are doing this thing, reheating the steam again and again, we are trying to use the temperature existed by the flue gases after burning in the furniture, as if we are using it to heat the steam in different heat the steam or steam water heater mixture into a different temperature in different heat exchangers like economizer, that's like preheater, like reheater, like this. Same steam is being used for a specific purpose to keep the temperature up to a certain desired limit and could keep the quality of the steam thus generated or thus generated from the water itself it up to a certain desired level, which in quality means the amount of heat present is the amount of moisture present in the liquid water before it is totally completely 100% converted to the heat to the moisture itself. So all these things, all this type of use, I mean the items are used in order to use in order to uh, utilize these gases, the heating feed water, to improve the higher efficiency and better economy of the total system of the boiler itself. Now, economy tubes are around 45 means 4.5 centimeter to 7 centimeter in outside diameter, made of naturally vertical coils of continuous tubes connected between inlet and outlet headers, with each section formed into several horizontal paths connected by 180-degree vertical path. So what do you mean by this thing is given here. Here there is a number of horizontal paths and there is a number of vertical paths. Here economizer size is around 5 to 7 centimeter, 5 to 7 centimeter the outside OD, and make in vertical coils of continuous feeding. This is the coil, which is vertical, the coil is itself vertical, and which is a continuous tube. There is no junction or connection in between, and uh, in between the inlet, this is the outlet, as well as this is the inlet itself, and uh, forms here a continuous section, which each continuous section formed with several horizontal paths. Each section, there is so many horizontal paths formed into several, have been connected by 90-degree vertical bends. Here we are having this 90-degree vertical bends like this, and it depends on the type of well and ash characteristic itself. The coils are installed at a pitch of 4.5 to 5 millimeter, means the difference between distance between this each individual coil is around 4.5 to 50 centimeter gap. The diameter is around 45 to 70, and more or less same is the difference distance between each individual tubes. Now, figure below shows an economizer coil and the temperature profile of the flue gases and air water heated to the saturation temperature. But first of all, the water is supposed to be heated to the saturation temperature, where in the temperatures it's supposed to be fully, it can absorb the maximum amount of it can absorb the maximum amount of moisture or maximum amount of vapor in a given volume. So the temperature is now the temperature, the economizer temperature profile of the gas or water heated to saturation temperature itself. This is a economizer coil itself, that is, which has a inlet heater, where is from through which the water goes and got the heated from the furnace itself, and it goes out in terms of is the outlet itself. This is the outlet heater, this is the inlet heater. Next, the volume. This is the mass of the water or specific heat of the water coming out, or specific heat of the water coming in inside. And it is the T saturated and T temperature of the feed water. Here, the temperature of the output of the water is has the saturated temperature of the water itself, and it is filled up with the inlet temperature is filled up water vapor air mixture, which is much less temperature than the saturated temperature itself. And over the coils, the flue gases that starts flowing. There is so a certain specific heat along WG, omega G, to certain specific heat outlet itself. The rate of heat transfer from the flue gases to the feed water itself is given by Q economizer, around the heat transfer to the economizer, omega G, the specific gravity or specific gravity of the water itself. CPG is the specific heat. G1 minus TG2 is the temperature difference between the coming in heat, temperature of the heated water heated temperature of the fluid at the inlet minus to temperature of the fluid at the outlet, or temperature of the fluid at the outlet minus temperature of the fluid of the inlet itself. This can be said that omega specific feed water specific weight of the omega of feed water, or specific weight of the gas, it's a gas or vapor itself, or equal to specific weight of the feed water and the specific heat of the feed water itself, multiplied by the temperature of the temperature of saturation of heat minus temperature of the feed water itself, say at the inlet itself. So we are having two factors like U0, H0, delta Tm, where delta Tm log mean temperature difference, delta Tm, delta T into I minus delta T into A, ln delta Ti by delta T, where inlet and exit of the temperature itself and the log mean temperature, but more or less this is the mean temperature difference. Which means Log mean is, on another sense we can say it's a mean temperature difference, but the total difference in temperature is not same everywhere, but we take a mean, and that mean is taken by here like this, where mm, now at Ti is equal to Tg. What is Ti? What is Te is defined here. Ty I is equal to Tg is the temperature of the gas itself minus temperature saturated temperature. Temperature of the gas means temperature of the flue gas itself minus the saturated temperature of saturation itself, and delta Tc is the temperature of the gas 2 minus temperature of the feed water itself. And the equation has another form like this. 1 by U0 A0 is equal to 1 by RAC AI H1 AI X0 KW 4 AIN H0 H0 F5 and H0 F0. Here H is all the enthalpies of at different places, enthalpy or amount of heat content different places, and multiplied by the constant heat express, and U0 is the overall heat transfer coefficient. HSC here heat transfer coefficient due to heat transfer coefficient due to scale formed on the inside of the tube. HI inside heat transfer coefficient. KW thermal conductivity of the wall side, inside heat transfer coefficient of the wall side. KW thermal conductivity of the wall material. Next, AI is the pi dn di li, where A0 n pi into d0 l. L is the length of one coil, L is the number of coil, and AI and AIM is A0 minus AI Tn ln log ln A0 by A1. That is the area mean area. XWM thickness of the tube wall. HF0 thickness heat transfer coefficient due to solid heat transfer coefficient due to solid ash and spot ash and soot. Heat transfer due to solid ash and soot on the outside temperature surface of the tubes, and H0 heat transfer coefficient of the outside film, and heat transfer coefficient of the outside film cache size, and if the resistance due to scale 1 by HCl and fouling 1 by HF0A0 are neglected, and if the wall thickness is small, the overall heat transfer coefficient is reduced to 1 by U0. Heat transfer coefficient is 1 by U0, 1 by H1 plus W by Km divided by H0. So what is going on here very clearly is the heat transfer coefficient. What is the heat transfer takes place in the supervisor? First, it is given as the quality of heat transfer, and the omega is the specific weight of the gas, weight per unit volume, multiplied by the specific heat of the volume, heat transferred per unit weight, multiplied by T gas in and T gas out, and that is the omega SW will feed water is equal to Cp FW is equal to feed water, also the specific feed water, and T saturation by T Fg, and U0 into A0 delta T1 into M, where delta T1 M log mean temperature difference itself. Now, what is delta T and delta T Lm? Delta T Lm is the log mean temperature of the fluid of heat water while going through the surface. So this is given by this particular formula, where Ti and T, there are two factors acting here. Ti is given by Tg1 minus T saturated, means temperature of the fluid gases by saturated temperature, and Tg2 temperature of the flue gas at inlet at the minus T temperature of the fluid heater itself. Thus, U0, thus the equation of heat transfer becomes like this. So it is taken into account radial film flight due to scale heat transfer from the scale in the wall. Inside heat transfer is the inside heat transfer coefficient that is different from one other. This transfer coefficient means the transferring different amount of heat, kilowatt, kW thermal conductivity of the wall material, AI pi di Inlet temperature, inside temperature, into square centimeter, pi di into L, A0 outside, A0 is outside area, and pi d0 L. D is the diameter of the outside, di is the diameter of the inside of the resonator coil itself. L is the length of one coil, L is the main number of rings, AIM, the log mean area, is outside area minus inside area, means area of the thickness wall divided by mean of log of inside area divided by outside area divided by inside area. So A1M, what is this going on here? It is Ky, heat rate coefficient of heat transfer coefficient, which is uh, log mean Ky, what is that? XW, heat transfer, thermal conductivity of the wall multiplied by the log mean of the area. The log mean area. Area, we are not, we are thinking that not uniform, that we are taking a mean area by using this formula where it is inputs are the cross section area of the outside minus cross section of the inside divided by log E by ln or log E by A0 by A1 itself. Thus, other heat transfer coefficient outside field, and if the heat transfer scale and fouling are neglected, considering them to be clean, and if the wall thickness is small, then the overall heat transfer coefficient is 1 by U0 equal to 1 by H1 plus XW by KW in plus 1 by H0. The gas side coefficient is much less than water side heat transfer coefficient. The gas side coefficient is much less than the water side heat transfer coefficient, that is H0 less than equal to H1. Hence, the coefficient of heat transfer or thermal enthalpy of water side is much less than heat transfer coefficient, and the heat mass gas side coefficient means outside the flue gases heat transfer is much less than the water side heat transfer coefficient. That is, outside is much less than inside. To compensate this, the water surface of the tubes may be fined to increase the transfer surface of the heat transfer, both gas and liquid flow under force convention, for which Nu F into Re into PR, where Nu, Nusselt number, Hd by Kf is equal to Hd divided by Kf, Re, Reynolds number, sigma T divided by Vf. Vf is the kinematic viscosity of fluid, and rho P, Prandtl number, Cp by mu F divided by Kf, where mu F is the dynamic viscosity of fluid, Kf is the thermal viscosity of the fluid line, and so the gases of turbulent, if the gases are turbulent, a Diffus-Boiler equation can be used to evaluate heat transfer coefficient as given with Nu 0.023 into Re to the power 0.8 into Pr to the power n, where n is equal to 0.4 if fluid is heated and n is equal to 0.3 if the fluid is cooled. So there is the heat transfer, different heat transfer coefficient from, it starts from the side that the heat transfer is takes with heat transfer coefficient from the flue side is much less than the heat transfer coefficient from the water side itself. So if to get the heat transfer coefficient means higher rate of heat transfer from flue gas to the gas inside, we have to provide number of fins over the outside of the tubes itself. Both gas and flue water are force convention, at which Nu is Nusselt number is equal to Hd minus Kf. He is the Reynolds number, sigma D divided by Vf, and Pr is the Prandtl number, Cp mu n divided by Kf itself, where Vf is the kinematic viscosity of fluid itself, and mu F is the dynamic viscosity of the fluid, Kf is the thermal viscosity conductivity of a fluid bed film, and if the gases are turbulent, then Rita's boiling operation can be used to evaluate steam transfer and it has to evaluate heat transfer coefficient as given below. Nu is equal to 0.023 RE into RE to the power zero point 0.8 PR to the power n, where n is equal to zero point 0.4 if the fluid is heated and n is equal to 0.03 if the fluid is cooled. With the help of equation 3 and 4, we can estimate, and from equation 1, the surface area needed can be ascertained, where H0 pi n pi d0, since feed water is flowing through the tubes at exit from the economizer uh, with water being saturated, omega fw is equal to n into pi d square di pi by 4 di v tw into vf, where di is the inside diameter of the tube, v velocity of the fluid at the exit, velocity of fluid at exit, and vf is the specific volume of estimated water itself. So velocity and divided by specific volume multiplied by n number of coils multiplied by pi d pi d4 by di squared, this total cross section of the inside area. So the water will be being saturated omega fw. When the clearance C is given on two sides of the gas duct of both B, then number of turns Nf if one coil can be estimated is equal to Nf equal to L by B minus 2F to C. If the vertical pitch or center to center distance of the consecutive horizontal tubes forming the coil P as per the figure on next page, then the height of the tract occupied by the economizer is equal to HECO Ni into P. The vertical pitch, center to center distance of the consecutive horizontal tube means total length of the tube as per the given figure. Then the height of the duct will be HS0, the number of coils multiplied by P. So total length space occupied by economizer will be the number of coils used and multiplied by the pitch itself. When the clearance is given on two sides of the gas duct with B, then number of turns Nf of one coil must be estimated from Ni L by B minus 2C, where Pfw velocity of fluid at exit and Vf is the specific volume of estimated water itself. Just 1 second. The economizer is generally placed between the convective supervisor. Economizer is generally placed between convective superheater and preheater. So this is the total height. HL is 10. This is the pitch between the two row of the superheater economizer tubes. Now let us go for the superheater. It is another type of heat exchanger in which heat is being transferred to the saturated steam to increase the temperature difference. The superheater is a heat exchanger in which heat is transferred to the saturated steam to increase the temperature. It raises the overall cycle efficiency. Now, Heat transfer to the saturated steam. Steam is saturated, its total volume it is in such a temperature, its total volume is to fully occupied with the steam vapor or vapor itself. Now, to increase the temperature, it is used at, at heat is transferred to the saturated frame. To increase its temperature, it rises the overall cycle efficiency. In addition, if in addition, uh, in addition reduces the moisture content of the last stage of the turbine and thus increases thermal internal efficiency. So what they are doing, they are transferring heat to saturated steam, which fully filled up with a particular volume of steam is fully filled up with the steam itself. There is nothing left, and it is fully converted to steam. And they're supplying and heating this fully converted to steam and rising the overall cycle efficiency itself. In addition, that reduces the moisture content of the last stage of the turbine and thus increases the turbine internal efficiency. So it is mostly one rise the temperature. Main motto of rising the temperature is to give more energy to the moisture itself and thus reduces any chances of to existence of boiling water inside the steam vapor path. And the moisture content in the last stage of the turbine and this rated increases the turbine internal efficiency itself. In modern utility high pressure boilers, more than 40% of total heat is absorbed to generate the high speeder boilers. More than 40% of heat is generated to absorb the steam tubes placed in the superheater, and so large surface area is required to be provided for superheater of steam. So what we are doing, we have to 40% of the heat we have to transfer from the flue gases to the steam itself to generate steam. Steam takes to generate the steam takes to the superheater. So large surface area is required to provide superheater heat. The largest amount, 40% of the total heat absorbed is being done on the superheater. So we are supposed to increase the maximum area on the superheater itself so that it can apply to increase its efficiency. Acha. Superheaters are designed as convective superheater. Superheaters are designed as convective superheater, radiant superheater, combined superheater means it is transferred by the conduction and convection. It's by conducting from the direct connection with the flue gases. As the flue gases are surrounding it, directly hitting the tubes of the supervisor, I mean the superheater, radiation, where it is not directly coming into contact with the tube. On the flames are now directly coming into contact with the tube, but it creates energy. That energy is being absorbed by the superheater itself. So there are three types of superheater: radiant or combined superheater, depending on the on how on long heat, depending on low heat, low heat. It is on how heat is being transferred to the gases to steam. Convective superheaters are located in the convectional area zone of the furnace, usually ahead of the superheater, either designed screen the convective superheater from the furnace reduction by a blank of water filled with tubes which are not provided, packeted them to form a combustion fuel and high efficiency, but also interpreted the slag particles and presented the sagging problem. The convective superheaters are often termed as primary superheater, where the saturated steam, the drum is admitted all through the convective superheater are often termed as the primary superheater, where saturated steam from the drum is admitted itself. Although the disposition of heating surface varies widely with the design of the temperature, a typical arrangement should be shown in figure next page. After uh, what what happens here? The convective storages are located on the convective area of the furnace, usually ahead of the storage earlier design. Screen the convective storages from the furnace radiation by a blank of water blank of water filled up with tubes which are not participated in from the version itself. These flames are highly temperature, but also intercept the low slag particles are provided on the sagging problem. These convenient superheaters once formed once formed termed as primary superheaters and then saturated convective superheaters are often termed as primary superheaters where the saturated steam from the drum is emitted. Whether the disposition of a high heating surface varies widely with the design of steam generator is typical arrangement is shown in the figure next page itself. After convecting supervisor CSF, the steam proceeds to the radiant supervisor RSH, which is placed in the radiant zone, which placed in the radiant zone itself. Radiant zone of the furnace near the water valve to absorb heat by the radiation itself. The steam leaving the radiant superheater goes to the T superheaters, where highly pure water is being delivered directly straight to the steam in such a quantity that the temperature steam after the last stage of superheater is the perfect superheater area does not provide the steam rate. The pendant superheater is a combined superheater in the sense that it reverses heat properly by convection and partly by radiation. The radiant and the combined supervisor together are often named secondary supervisor, named as secondary supervisor itself. So what is going on? The secondary supervisor and primary supervisor, the steam leaving the second radiant supervisor goes to the desuperheater, where it is mixed with highly pure distilled water is sprayed to steam in such a quantity that temperature stream after the last state of superheating does not exceed the rated rate. The pendant superheater, the combined superheater indicates that it receives heat partly by convection and partly by the radiation. Radiation and conductor superheaters, they together are often termed secondary superheater itself. The energy balance of the consecutive superheater gives QCH QCH is equal to omega G by CPG TG1 minus TG2, where or omega S is equal to H2 minus H1 equal to U0 into say A0 into delta E log mean, where U0 is equal to 1 by H1 energy between the conservative supervisor gives us QSH omega G CPG and TG1 minus TG2 omega is H2 minus H1 omega 0 H0 delta T log mean, whose 1 by H0, 1 by H is equal to 1 by H1 plus XW by KW is equal to 1 by H0. H0 is a pi n pi d0 L. L is the length of the coil, n number of coils required since it is a gas to gas heat transfer with low heat Li steam and low H0 outside gas. The overall coefficient of heat transfer is given as Ws is equal to n into pi by 4 di square itself. Pi by 4 di square multiplied by Vs by Vg, where Vs is the average velocity of the steam in the supervisor. For intermediate pressure boilers, the steam velocity may be about 22 meter per second. Just 1 second. Here is taken into account. Now Ws or omega s is equal to n pi by t. N is the number of coils. N pi by 4 di is the internal diameter of the coil. So total inner area of the coil itself multiplied by Vs, the average velocity of steam in the supervisor itself. And in intermediate pressure gauges, the steam velocity may be about 22 meter per second. For high pressure boiler, it is about 12 meter per second, and very high pressure boiler it is 10 meter per second, approximately. Superheater and superheater stresses are withstand them better. The larger diameter have larger steam flow and pressure drops and are easier to align. There is no number of coils needed for flow is estimated from the above equivalent and the length of one coil L is determined after A0 as computed from equation 2 above. So number of coils needed for the flow estimated about the equation 2 here, and the length of one coil is determined after it being computed from the top. And resident superheater located in the resident area, radiant superheater in the area of the furnace permits greater heat consumption by the radiant mode of the heat transfer itself. QRSLM sigma AT into EV into T omega T r to the power 4 minus TW to the power 4 and equal to WSH3 minus H2, which is equal to 3, where sigma is the Stephen Boltzmann's constant, which is equal to 5.67 to the power minus 8 omega in watt per square meter per kilowatt to the power 4. 80 total surface area of the supermeter exposed to the flame outside in square meter. F feed water feed view factor with respect to flame and water. TF flame absorbed absolute temperature. K and T boil are well defined. TW wall absolute temperature K. Now TW is equal to T saturated per 50 75 degrees centigrade. TF greater than equal to TW. QRSH is more or less equal to TF to the power 4. Now as TF is not strongly dependent on load, as the steam flow increases with load, the heat transfer per unit mass of fluid decreases. So QRS sigma 80, where sigma Stephen Boltzmann constant 5.67 to the power minus 8 W per meter square to the power 4 AT. Total surface area of the superheater exposed to the flame in M square. FTW view factor with respect to the flame and wall. View factor with respect to flame and wall. TF flame absolute temperature in degree Kelvin. TW wall's absolute temperature degree Kelvin. So TI and TF. And now TW temperature of the wall is equal to temperature saturated water temperature of the saturated heat plus 50 degree to 75 degrees. Since temperature of the fluid is greater than equal to temperature of the water itself, then QRS is equal to more or less proportional to TF to the power 4. And as TF is not strongly dependent on load, as the steam flow increases with load, the heat transfer per Emitted mass of fluid decreases itself. Okay, so I am finishing here now. Over here.